You step onto the platform, feel the concrete rumble beneath your boots, and within seconds, a 10-car train glides out of the dark tunnel, hissing to a stop as the automated doors slide open. You step inside, grab a seat, and take it for granted that 30 seconds later you are hurtling through subterranean darkness at 50 miles an hour. But look up at the curved ceiling, because right above you sit thousands of tons of soaked bedrock, gas mains, live electrical feeders, sewer pipes, and skyscrapers bearing down with millions of tons of force. Common intuition tells you that digging a massive void through soft soil beneath a city should cause streets above to collapse into a sinkhole, and driving a train under an active river should turn the tunnel into a flooded tomb the second a seam cracks open. Yet millions of commuters travel through these subterranean arteries every day without giving the physics a second thought. The reality is that subway tunnels are hyper-engineered pressure vessels fighting a non-stop war against tectonic overburden, crushing groundwater pressure, air stagnation, and thousands of volts of live electrical current. To understand how a subway tunnel survives beneath a city, you first have to look at how engineers carve the earth open without bringing down buildings overhead, because historical and modern methods are completely different. In the early 20th century, cities built subways using cut and cover, which was open heart surgery on the street grid. Contractors drove steel soldier piles along curb lines, tore up asphalt with steam shovels, and excavated deep open trenches outside storefront windows. To keep the city moving, carpenters laid timber decking across the trench so traffic rumbled overhead while miners shoveled dirt 20 feet below in the dark. Once the trench reached track level, crews poured concrete box culverts, waterproofed the exterior with asphalt pitch, backfilled the soil, and repaved the street. Cut and cover works for shallow lines, but in a modern city packed with high-voltage conduits, fiber optics, water mains, and steam pipes, tearing up streets is an impossible, multi-billion-dollar nightmare. That is why modern deep-level subways bypass the surface world entirely by plunging 60 to 200 feet into bedrock using the tunnel boring machine. A modern TBM is a self-contained subterranean factory stretching hundreds of feet behind a circular cutting face matching the finished tunnel diameter. At the front sits the rotating cutter head, an immense steel disc studded with hardened tungsten carbide cutters exerting thousands of tons of hydraulic thrust against the rock face. As the cutter head rotates, these discs fracture the rock by rolling across it under pressure, chipping off spalls rather than grinding it into dust, while muck buckets scoop debris through openings onto a conveyor belt carrying crushed earth out of the tunnel. The real engineering genius of a modern TBM reveals itself when it encounters the ultimate tunnel killer, which is not hard rock, but soft, waterlogged silt, sand, and liquid mud below the water table. If you simply dig through saturated gravel, the excavation face immediately liquefies and collapses inward like a sandcastle hit by a wave, swallowing streets above into an instant crater. To prevent this, engineers deploy earth pressure balance or slurry TBMs that seal the cutting chamber into a hyperbaric zone. By pumping bentonite slurry or polymer foam into the chamber, the machine creates a dense paste pushing forward with an exact hydraulic counterforce matching the weight of dirt and groundwater, balancing subterranean pressure until permanent support is locked in place. That permanent support happens automatically inside the rear skin of the machine using precast concrete rings. Once hydraulic thrust rams push the cutter head forward 5 feet, the rams retract, and a vacuum erector arm picks up curved precast concrete segments cast in precision surface molds. Working in a tight circular choreography, the erector arm positions 6 to 8 of these heavy segments against the excavated perimeter, interlocking them with tongue-and-groove joints and bolting them into a rigid ring capable of withstanding hundreds of tons of lateral pressure. As the TBM pushes off the leading edge of this new ring to advance, fast-setting grout is injected under high pressure through the trailing shield into the void between the ring and raw earth, locking the ring against bedrock so no surface foundation settles. Once the physical tube is locked in place, the battle shifts to the single most relentless enemy of subterranean infrastructure, which is groundwater. There is a common misconception that subway tunnels are hermetically sealed like submarines with zero water intrusion, but experienced tunnel contractors will tell you that every underground subway system in the world leaks on purpose. Water weighs over 62 pounds per cubic foot, meaning that when a tunnel dives 80 feet below the water table or crosses beneath an active riverbed, groundwater exerts an immense hydrostatic head against every square foot of the tunnel exterior. If engineers tried to build an impervious, zero-leak barrier across miles of deep tunnel, that crushing hydrostatic pressure would build up against seams until it fractured the concrete or blew out expansion joints. Instead, the tunnel is engineered with a multi-tiered hydraulic defense that controls water ingress rather than fighting it with brute force. Between every concrete ring segment, contractors install elastomeric and hydrophilic rubber gaskets set into recessed perimeter grooves. When moisture reaches these hydrophilic gaskets, a chemical reaction causes the synthetic rubber to swell up to 400% of its dry volume, packing the joint tightly and blocking water infiltration. For the small percentage of nuisance seepage trickling past seals, the tunnel floor is cast with drainage troughs sloped downward along the tracks, channeling infiltrating groundwater by gravity into deep sump stations excavated at the lowest topographical points of the line. Inside these deep sump chambers sit redundant industrial centrifugal pumps controlled by intrinsically safe float switches and ultrasonic sensors. Even on a clear day with zero rain outside, an average metropolitan subway discharges millions of gallons of groundwater seeping through tunnel walls, pumping it up vertical riser pipes into municipal storm sewers before it touches rails or electrical gear. At shoreline boundaries, where subway tubes dive beneath rivers, engineers install the ultimate catastrophic failsafe: massive motorized floodgates. These 30-ton steel and concrete guillotine bulkheads sit recessed in the ceiling and portals, rolling shut in under 60 seconds to hermetically seal the underwater section if a ship anchor punctures a tube or a storm surge breaches an entrance. With the structural shell secure and groundwater controlled, the tunnel must now deliver enough electrical muscle to launch a 400-ton train down the line, and doing that underground requires a very specific traction power setup. Unlike surface railroads using overhead catenary wires hanging from steel masts, underground subway tunnels are severely constrained by vertical ceiling clearances. To run overhead wires, you would have to excavate the entire tunnel bore 2 to 3 feet taller along its entire length, multiplying excavation costs and structural risks exponentially. Instead, subways rely on the electrified third rail, an uninterrupted steel or aluminum rail mounted on porcelain insulating pedestals running parallel to the tracks just inches above the ties. This third rail carries between 600 and 750 volts of direct current, fed by underground traction substations that step down high-voltage alternating current from the grid and convert it into clean DC power using silicon rectifier banks. Mounted beneath the wheel, assemblies of every car are spring-loaded collector shoes riding firmly along the contact surface of the third rail, drawing thousands of amps to supply traction motors. To protect track workers from touching lethal voltage, modern systems encase the third rail inside fiberglass and timber guard boards, with the collector shoe either sliding along the bottom of the rail in an underrunning setup or slipping through a protected side slot. The most fascinating part of subway electrical engineering is the return path, because electricity cannot flow unless it completes a closed loop back to the substation. Many people assume return current simply grounds out into the dirt, but raw, direct current bleeding into the earth would rapidly dissolve utility pipes through catastrophic galvanic corrosion. Instead, the 2 steel running rails serve as the dedicated neutral return conductor. The heavy steel wheels roll across the running rails, collecting spent current from traction motors and sending thousands of return amps back through the rails, welded and bonded with braided copper jumpers. To allow these running rails to carry massive traction return currents while simultaneously carrying delicate low-voltage signal frequencies used to detect train positions, engineers install specialized filters called impedance bonds that separate propulsion power from automated signaling without shorting out. Finally, you have to look at how thousands of human beings survive inside a concrete tube with zero natural sunlight and zero natural airflow, because a subway tunnel is an extreme thermodynamic environment. Every time a subway train breaks into a station, its friction brake pads and dynamic braking grids convert immense kinetic energy into heat, while passenger body heat and air conditioning compressors dump continuous thermal loads into the tunnels. To breathe, the system takes advantage of the piston effect. As a train hurtles through a single-track concrete tube at high speed, it pushes a massive wall of compressed air forward while pulling a strong vacuum behind it, acting like a giant mechanical syringe plunging through a cylinder. To prevent this piston pressure wave from blowing platform doors open or knocking commuters off their feet, civil engineers construct vertical blast relief shafts right before every station entrance. As the train approaches, compressed air diverts upward into the relief shaft and exhausts harmlessly out through sidewalk grates on the street above, drawing fresh outdoor air in through adjacent intake shafts as the train pulls away. If a mechanical fire or electrical short fills the tunnel with dense smoke, the life safety system immediately overrides natural airflow. Enormous emergency jet fans embedded in mid-tunnel fan plants spin up within seconds, drawing toxic fumes away from the stalled train and exhausting it to the surface while forcing fresh, positive pressure air into designated passenger evacuation tunnels so commuters can walk safely along catwalks toward illuminated surface exit doors. From the pressurized cutter head of a TBM balancing tons of saturated silt, to hydrophilic gaskets swelling against crushing hydrostatic head, to impedance bonds separating traction current from digital safety signals, an underground subway system is a masterclass in heavy civil engineering and building science. It takes the most punishing subterranean forces on Earth and turns them into a smooth, seamless commute that millions of people rely on every day without ever realizing the incredible engineering holding the world above their heads.